All right, so now let's go over to one of my favorite topics, which is context-free grammars. And it's kind of funny that we're doing that today because in 1090, what we did today is we skipped syntax, and what we skipped was looking at context-free grammars. So those of you who are in 1090 are going to learn about context-free grammars here, despite the fact that we skipped it. All right. So what is our goal here? Our goal is to, when you do type in Word and it underlines things in green because your grammar's not good, what it's doing is it's parsing it. And so what we're going to have here, this is a grammar, and this grammar can generate different strings. And so we're going to say it's anything with that's a valid expression can be generated by this grammar, right? And so let's kind of go through how that works, right? Here's my grammar. I'm saying, well, what is a valid expression? Well, an expression, I can say, oh, what's an expression? And I can replace an expression with term plus expression, right? So what is an expression? Well, it's a term plus an expression. Great. Well, what is this expression? Well, an expression could also just be a term, right? An expression is either a term plus an expression, or an expression is just a term. So here I took this expression, I converted it into term plus expression, and then that one I converted into a term. So now I have term plus term, right? And then we say, well, what is a term? Well, a term is either a factor or it's a factor times a term, right? In fact, what is a term? An expression is a sum of terms. What is a term? It's a product of factors, right? So what is this term? It's some factor times a term, right? And what is this term? Well, it's a factor, right? Now, oh, what's this factor? Well, what's a factor? A factor is either an integer or it's an expression inside of brackets, right? So I say, hey, this factor here, what is it? Well, it's an integer, and 0 is an integer, so we're good. What about this factor over here? Well, it's a 1. That's fine. What about this factor over here? Oh, we haven't done term yet. This is still a term. What's this term over here? Well, terms could just be a factor, right? So now what's that factor? Oh, it's a 1, right? So that gives me here what we wanted to know. Is this an expression? And we say, yes, it's an expression. Why? Because from expression, I derived your string. People kind of buy that? Right? And sometimes what we do is this is sort of, you go from line to line in this method. And whenever you have, these are called non-terminals. Whenever you have a non-terminal, you can use a rule to replace it with something else, right? Until everything is just terminals, because what's in purple are terminals, right? So another way of thinking about it is we can build a parse tree, right? So here, what's an expression? It goes to term plus expression, right? And what is this expression? It goes to term. And then this term goes to factor times term, right? And this term goes to factor, right? And this term goes to factor, and all of these factors go to various integers, right? So this is a parse tree. People buy that?
Yeah.
All right. Now, you might think that this would be a better parse tree, right? This is a funny parse tree. I like this parse tree better. Why? It says, what is an expression? It's the sum of terms. What is a term? It's the product of factors, right? So I think this is a prettier parse tree, but it just doesn't quite come from this grammar. All right. So here's a grammar that says what is an expression? Well, it's either a term by itself or it's the sum of a bunch of terms, right? And what's a term? Well, it's a product of a bunch of factors. But the problem with this grammar, well, this is an infinite rule, and you're only allowed to have finite rules, right? So this is a proper grammar because it doesn't have infinite rules. Well, this is sort of an infinite description of a rule, right? So that's not really a real grammar. All right, and here's another string. All right, here's some big scary string down here. And why is it an expression? Well, the whole thing's expression because it's the product here, term plus term. It's the product of two terms, right? And this whole thing, why is it a term? This whole big like ugly thing here, why is it a term, right? It has brackets around it, right? Well, it's a term because it's a factor, a single factor. And why is it a factor? It's because it's an expression inside of these outer brackets, right? Does that make sense? So syntax means the grammar, if the grammar generates a string, if and only if the string is in the language, right? Sort of if and only if a computational problem is going to say yes, right? So with grammars, we more think about it as generating strings, right? While computational problem, we think about more as you give me the string and I say yes or no. All right. Semantics is now I want to have some meaning. What does this string mean? I had that big ugly string there. Do we get any meaning? Well, having the parse tree from the grammar somehow gives you more meaning than you had before, right? In fact, when you're trying to understand an expression, in order to understand it, what you do is you more or less you build a parse tree in your head. All right? And what do you do with this parse tree? Well, you can use it for lots of reasons. You can help to know, is it a proper string? You can use it to evaluate the string, to compile, to write a compiler from Java into machine code. There's lots of things you can do, right? Or Microsoft Word, as I said, it takes sentences that you type, and if it can't parse it, then it underlines it in green and says, we don't like your grammar, right? I love this algorithm, so I used it to build the compiler with my son into machine code. All right. So let's now define what a context-free grammar is. You can have terminals, which are actual letters in your string, maybe A, B, C, 1, 2, 3, right? Characters that are actually in your string. The capital letters are for concepts, and they're called non-terminals, and they are used to generate more strings. And then we have rules. A rule would say, if you have anywhere you have a non-terminal A, then you can convert it into little a, big A, little b. Or there's or here, or you convert it into this longer thing, right? So now, non-determinism, you all know about non-determinism here, right? Which rule do you use? Well, yeah, you're either sort of looking at the string you're trying to generate and you magically can figure out which rule to use, or you can suppose you have a fairy godmother which tells you which rule to use, right? A grammar also has the start symbol, start non-terminal. So in our last example, we were starting with expression, right? And when do we stop? When we stop when there are no more non-terminals, right? When we only have characters from the alphabet, all right? So what are various grammars? There's a grammar for English. There's a grammar for Java. All right, here's a very silly little grammar. And I'm just using it to kind of demonstrate some concepts. We want to know, what does it generate? Well, we start with start symbol S, right? And from S, you can either go to an A, a B, or a D, right? So let's just guess now. Let's start going to A and see what happens, right? We're going to go to one of these three. And now, all right, so if all the characters in the string become non-terminals, then we stop, right? So here, what does A go to? Well, A can go to a character A, right? In which case we generate that. So we actually, this grammar can generate A, little a, right? A little a is a proper string of our language. What about D? D doesn't go anywhere. It kind of dies, right? So it doesn't do us any good whatsoever. So it doesn't generate anything. And what does B generate? Well, you can see B keeps putting out little b, big B, little b, big B, but never does it get rid of that big B, right? So that is not actually generating anything. So the only string that this grammar generates is the single character A. People kind of understand that funny example? Noam Chomsky. If you don't know Noam Chomsky, you should read about him. He's this, you know, I would have voted for Bernie Sanders if you haven't figured that out. But I voted for Hillary because I couldn't vote for, no, not Hillary. I voted for Hillary last time. Who's the dipwit I'm voting for this time? Was Biden, right? But I would have preferred to vote for Bernie. And Chomsky, if you think Bernie is left, then Chomsky is even further left. He's as left as you can. He's one of the most famous sort of really left-wing thinkers, and he writes fantastic, he gives fantastic lectures.
Is he a communist?
What?
Is he a communist?
Yeah, you know, I'm not always quite sure what communist means versus socialist versus, right? But he certainly wants the poor of the world to be empowered, and he wants the poor of the world to eat.
Okay, fair enough.
So anyway, why did I bring Chomsky here? Is, well, because he pretty much invented everything we're talking about in this section. It's all Chomsky's work. I think he started as a linguistic for his graduate school, and so, and this, what does this say? Here's a good quote for today. It said, education is useless. The only purpose of education is to torture you and decide who will be willing to work for the man and who's not willing to work for the man.
Oh, damn.
All right, so anyway, he's a university professor, so he's allowed to say that. All right, so let's talk about the Chomsky hierarchy. Remember, we talked already about strings that can be expressed by regular languages, right? A DFA can do them, an NFA can do them, regular expression can do them. And we sort of proved that 0 to the n, 1 to the n can't be done by a regular expression, right? But he defines this idea of a context-free grammar, and we're going to see that 0 to the 1, n to the 1 is trivial to do with a context-free grammar, right? But here's another string, 0 to the n, 1 to the n, 2 to the n. That cannot be done by a context-free grammar, right? And the proof that you can't do this is really harder than we ever want to do. But what I'm going to do is I'm going to do some hand wavy and convince you that it can't be done by a grammar, context-free grammar, all right? And then, right, then you have a bigger class of things that can be computable, decided by Turing machines, all right? So before we go on too much, let's talk about context-free grammars versus context-sensitive grammars, right? A context-free grammar says that if you have this B, capital B in here, how you convert the capital B is not influenced by the A and the C on the outside. All right. While a context-sensitive grammar, how you convert the B is dictated by whether you have an A and the C on the outside, right? So you'll have rules that say if you have a D and a C on either side, then you can convert something. And if you don't have D's and C's on the either side, then maybe you can't convert it. All right. But I have slides that do exciting things about context-free sensitive grammars, but we're going to cut it all out. All right. So here I just want you to know the context freeness comes from how I convert this B, how I convert this C doesn't have anything to do with the context that the C is in. All right.
Yeah. I have a question. So would it be easier to process a string that's context free but has a lot of terms, or a language with context, right? But you'll have it's just harder to process.
Right. So context sensitive grammars are very powerful. They're more powerful than Turing machines. Well, I guess they're as powerful as non-deterministic Turing machines. So that's partly why we're not covering them, because it's a much harder problem. You have to deal with the halting problem and things, right? Context-free grammars live down here, and so we're going to be dealing with those.
Sorry. Why can't Turing machines exactly compute them again? That's a little confused.
Well, Turing machines can handle regular expressions. Turing machines can handle context-free grammars, but context-sensitive grammars, they're as powerful as knowing whether your Turing machine halts. So
okay.
To know whether or not I can parse using a context-sensitive grammar, well, that's undecidable. It's as hard as knowing whether a Turing machine halts.
Gotcha. And regarding the complexity classes, is there any way like you could turn a context-sensitive grammar to like a context-free grammar? And then,
no, because there are problems that are much harder, right? Context-sensitive grammars can be talking about Turing machines, and context-free grammars can't talk about Turing machines.
Gotcha. Oh, thank you.
All right. Right, this is kind of what I was saying. Every Turing machine must halt on every input to give the right answer, and the halting problem lives up there, and these enumeration, these other problems live up there, and context-sensitive grammars live up there, and we don't want to deal with any of that. All right, so let's quickly get away from that and just go back to context-free grammars. Now, some context-free grammars have ambiguities in them, and some of them are free of ambiguity, right? So what does this mean? Well, if my grammar said, well, a string is either 0 or it's 1, or it's s plus 0, the sum of two strings, or it's the product of two strings, right? That's my grammar rules, right? Can I parse this? Yeah, definitely, right? An s is the sum of two s's, an s is the product of two s's. Each s is a 0 or a 1, right? So this grammar can parse the string, right? But look here's another parse tree for the same grammar, same string, right? We could first do the multiplication and then we do the addition, right? So here are two parse trees parsing the same sentence, and we call that ambiguous because we don't know. Well, when you gave me the string, is your intention this or is your intention that? And these two seem to have very different meanings. So we don't like this grammar. Why? Because it has two very different meanings when we don't want to have different meanings, right? And the problem with ambiguous grammars is that you can have different interpretations of them and people can be confused. All right? So that's why we did this whole expression to term, term to factor, factor to expression in brackets, because this grammar is not ambiguous. It always parses. The parse tree always looks exactly the same. And this grammar, if I do expression is a sum of terms, then it's still, right? It does it uniquely. All right, so somehow I feel we did this recently. Somewhere recently I've done this grammar with people. But here's a grammar that defines Java, right? What's an if statement? Well, it's an if followed by a Boolean in brackets, followed by a then, followed by an operator, right? So this is quite a reasonable grammar for parsing your Java. And when I wrote a compiler, these might be the exact rules that I wrote down, and I used those to parse my grammar and convert it into machine code, right? But the problem with this grammar is that it turns out to be ambiguous, right? So if you look at it, if then, oh, it's here. Here's the problem. I'm doing a while, right? And so is this line, is the I equals I plus 1, is it within the while loop or not, right? And when you do the parsing of this, right, we can parse this using all these rules, right? Right, I don't remember this grammar, right? But the point is that you can parse it different ways, right? Here, in fact, maybe right here I'd say, well, it is an operation. An operation is a while followed by a Boolean followed by an operator, right? So now what's my operator? Well, operation, well, is it one line or is it, how does this guy fit into it? Right? Does that, people kind of follow this? Right? But what the user should have done is put brackets around this, right? If you put brackets around it, right, then you can go from one operation to a string of operations, and you can parse both this guy and this guy. People following that a bit? You might have seen these examples in your first year coding class, right?
Mm-hmm.
Right? So yeah. If we have this grammar, right, well, where did the second operator go? And well, it should go up here, right? And so really the code is doing this, right? The second operator is inside of this if statement. It's not inside of the while statement. So I guess here's another sort of example, and it says op, it can't generate more than one operation without putting brackets around them, right? So if I asked, hey, can you build me a parse tree for this from this grammar? The answer is no, because if I start from op, how do I get more than one? How do I get an ops, right? All I can get is ops with brackets in them. So, oh, here's the other classic ambiguous, right? So this else if, does the else if go with this if or with that if, right? So what is an operation is an if statement. An if statement is a Boolean, if Boolean op. Well, this Boolean is easy that, right? And now what's this op? Well, this op could be an else if, right? And if the else, so then, right? Else if is going to be if this operation, then this op, else that op, right? That looks great, right? So that looks like a great parsing, right? But we could have a second parsing, right? These two strings are, You know, in Java, blank spaces doesn't matter. If you're doing Python, it treats this blank space as meaningful, but Java doesn't treat this blank space as meaningful, right? So you can have a different parsing here where you have the else if, the first if is an if else, right? People follow that?
Which parsing are we expected to do?
Right now, I'm giving you kind of a discussion about the issues, right? Ambiguous is an issue, and I'm kind of giving you different grammar, little pieces of grammar to see how to do it. But you know, we're going to be learning more concrete things now. I don't know. Right now we're just discussing this issue of ambiguous, and you know, we haven't spent too much on the details of this. If we want to focus later on the details of this, we can. Right now, I'm just saying this looks like a reasonable grammar, and it doesn't distinguish between this and this, right? And that is a problem that people have in computer science, right? If you were to type this in Java without the brackets, I'm not sure what the compiler might do. The compiler might give you a warning and saying, hey, dude, I don't know. It's ambiguous what you mean. Right? Here's another grammar, right? And this grammar is a grammar of English, right? And you learn this when you learned, well, when I learned German and Spanish, they taught me the grammars of German and Spanish, and they more or less taught it using these context-free grammars, right? What is a sentence? It's a noun phrase followed by a verb phrase, right? What is a noun phrase? Well, you know, when you go through it, what the grammar is. And I'm just here giving you an example, right? The girl hit the boy with the flower, right? So everybody visualize what you think that means. The girl hitting the boy with the flower. Well, it could mean that the girl hit the boy. Which boy did she hit? She hit the boy with the flower. So here's the boy with the flower, and here's the girl hitting the boy that has the flower, right? And don't you love this? I put all these together. I took the flower and I put it on top of a boy, and I took the boy and I took it on top of a girl. So this is my picture, right? And what does this say? This says the girl hit the boy. We don't care which boy, but how did she hit him? She hit him with the flower, right? So it's not clear whether with the flower refers to the boy or refers to hit, right?
There'd be like punctuation to tell the difference, or some type of like a comma or something should be added there to.
Yeah, you know, I'm not an English major. I think if I was writing this myself, I would sort of break it up somehow. I might say, if I wanted to say the boy with the flower, I might say the girl hit the boy that was holding the flower. Right? Who was holding the flower, right? Or if I wanted to hit, I might say, I don't know, the girl hit the boy, and man, she hit the boy with the flower. I don't know. I'm not an English major, right? So I'm just saying that this is a problem.
Okay. Yeah.
Right? So why is this and you know, in English, this is ambiguous. Right? You can read this either way. And why is it ambiguous? As well, the grammar is ambiguous, right? So we could go in here and figure out where is the grammar ambiguous, right? Can lead to different interpretations of the string. All right.